Hello again, everyone. Welcome to our continuing discussion of the easiest topic this semester. That is the topic of descriptive statistics. We will be spending the rest of the semester with the topic of statistics, also known as prediction in this topic of business analytics. In statistics, we're looking at the collection, analysis, communication, and interpretation of data, or simply data analysis. In statistics, we make data meaningful. We bring meaning to data. Statistics comes from the Latin word for state or government. Okay, statistics or numbers have been collected from the beginning of time, the beginning of civilization. On the Egyptians, on the papyrus scrolls, there are various statistics taken and captured. What two things have are the reasons why governments have collected statistics from the very beginning of civilization? Two same unfortunate reasons. Number one, to know what kind of tax base they have to generate taxes based upon. And the second reason is to know how many people they can conscript an army from. Two unfortunate reasons why statistics have been collected from day one. The modern statistics are based upon the work of John Galt and Edmund Halley of Halley's Comet fame, where they developed the two really useful life tables. For them, people were issuing insurance companies, governments were issuing annuities, and they had no idea whether they're going to make money or not. And a lot of them lost money. It wasn't until they generated the forms of these life tables that we used for our insurance problems. And John Gaunt and Edmund Halley were the first people to do that with some actual live data of merit. Another excellent statistician was Florence Nightingale, the nurse with the lamp. She brought back data on the Crimean War and showed that more people were dying from disease than were dying from wounds that they were incurred in battles. Crimean War was fought, I think, a little bit before our Civil War, a little bit before our Civil War. All right, so our topic for today is descriptive statistics, where we organize data and summarize data and present data. And we've seen that we will be dealing with qualitative data and quantitative data for the rest of the semester. When we have qualitative data, if the question that was asked over and over and over again when the sample or census was conducted, if the answer to that question is not a number that can be that you can do arithmetic with, if it's anything else, it's qualitative data. Qualitative data, some of it is nominal data. These are just names or categories. And some of it is ordinal data. In other words, it can be ranked. The brand of gasoline you purchased is a nominal. It's just a name. It's Costco or whatever. Okay, at the end of the semester, when you're asked to brutally evaluate me, you will be given your choices of 1 through 5. A 1 means what? Bad. A 2 means poor. A 3 means average. A 4 means good. A 5 means excellent. Those are, in fact, examples of ordinal data. All those, the 1, the 2, the 3, the 4, the 5 are placeholders for the words, you know, bad, poor, okay, good, or excellent. When we rate things, a score of 4 does not mean you're twice as good as a score of 2. It doesn't mean that. You can't really do arithmetic with those. So when you do evaluations and rate people on a scale of 1 to 5 or 1 to 10, technically that is not quantitative data. So nominal data are names, things. Ordinal data, things that can be ranked. Like what's our threat level at the airports these days. They used to have the old method of a red and an orange and a yellow. And so you ask what is the level now, and it's orange. You know, that's not as bad as a red, but worse than a yellow. So it's still qualitative data that can be ranked. That's called ordinal data. We've talked about the quantitative data. Ratio data is all we're using for the rest of the semester. And interval data is mainly for temperatures. We're not dealing with that. Census is when we go out and ask everybody in the population a question. We try to do one of those every 10 years. We don't do it very successfully because the people are moving targets. Some of them don't want to be polled. They don't want to have the census taken. And people move around. We have presentation methods. We have line charts, bar charts, pie charts, and pictorial charts. Now, a pictorial chart, the market segment that a various gasoline would have, there'd be different sizes of gas pumps. Try not to use pictorial charts ever. They're misleading. So we try to do either line, bar, or pie charts. We have frequency distributions, as we've seen, relative frequencies. When we rank things, we get a Pareto. We've seen histograms, which is our bar chart for quantitative data. We can describe histograms with the words symmetric, skewed, normal, uniform, unimodal, and bimodal. Stem and leaf box plot, 5 number. We'll do an example of that momentarily. And we'll come back to these procedures. Okay, let's introduce these population parameters. When I go out and do a census, then I need the following, need you to memorize the following 4 symbols for the rest of the semester. Cap N, big N, is the population size. If I do a census of quantitative data, then I get the mean, the median, and the mode, same as always, but mu is the symbol for the average of everybody. Mu is the average of the entire population. If I have quantitative data and I want to do a measure of dispersion, then I have, of course, the variance. The variance is the squared differences of each of the individuals in the population away from the mean, divided by the population size. We also have the standard deviation, the coefficient of variation, and the mean absolute deviation. So, cap N, mu, sigma are our symbols for quantitative data. For qualitative data, it's cap N and P. P represents the proportion of the entire population that has some attribute. If you're trying to figure out which symbol is it, first question, did I ask everybody? Yes, census. No, sample. Then the question is, was the data quantitative or qualitative? It seems very easy to figure out, doesn't it? Let's try. What symbol am I? Now you're going to be able to read a paper, a newspaper, or watch TV and be able to say what it is that has just been reported. Let's see how you do at this. A recent CNN poll indicated 72% surveyed are in favor of a proposed change in capital tax gains. Okay, what did I just say? First question, what? Did I ask everybody? Did I ask everybody? I don't remember them calling me. Make it personal. Did they call me? No. It's a sample. What question did they ask over and over? Oh, 72% is a number. Oh, it's quantitative. Don't be a road runner. Be a sloth. Reenact it. Hello. Calling for CNN. Yeah, I know it's dinner time. Yeah. Oh, sure, that's anatomically impossible for me to put that there. Just reenacting, role playing. Hello, CNN calling. Yeah, I know it's dinner time. Yeah. Are you in favor of the proposed tax change? I'll take that as a no. Yes or no? I get back yeses and nos, right? It's qualitative. Qualitative sample, what is it? X bar. Proper symbol would have been, oh, I'm sorry. I screwed that up on purpose, of course. P hat. Can I do arithmetic with yeses and nos? No. You know, are you in favor? Yes or no? Yes or no? Yes or no? So it's qualitative data from a sample. It's a p hat. The window sticker on the Yugo sedan listed 40 miles per gallon in the city. Must be 30, 40 years ago now. There was the automaker from Yugoslavia tried to enter the U.S. market with the Yugo. It was basically a riding lawnmower. But it wasn't very powerful. But that's all I can afford on my salary. So I'm looking at a used Yugo right now. And I saw that the sticker on the Yugo listed 70 miles per hour. 70 miles per gallon in the city. Ooh, good gas mileage. Hey, did they test every car? Well, they tested every car that they tested, right? So it gets confusing, huh? They tested every car that they tested. No, when they're going to make a study and then extrapolate it to all other cars, it's a sample. It is a sample. They don't test every car. The Yugo I looked at had a mileage of 6 on the odometer. Did they test that for mileage? No. So no, all the cars you find in the showroom, none of those have been tested for mileage. So it's a sample. And what question did we ask? What's your mileage? 38, 42, 40. Can I do arithmetic with 38, 40, and 42? Yeah, I can. It is a X bar. The mayor won the election with 52% of the vote. Did they count everyone? They counted, oh no, they didn't count. So some people didn't vote, right? Do we care about those people? We don't care about those people at all. Screw them. Okay? They don't have any bearing on who gets elected. So, did I count everybody? Yeah, I counted all the votes. And I get, what was the question I asked? Who'd you vote for? Smith, Jones, whatever. I get names. Are those things I can do arithmetic? No. This is a P. It's a P. The proportion of the entire population who voted is 0.52. Michael Jordan has the highest career average of any player ever. Number 1. The person who's number 2 surprised me. Anybody know who the second all-time leading scorer in the NBA is? You know, I thought it would have been, Wilt or Kareem maybe. But then they both had long careers where they went defensive, You name just an offensive machine, just nothing but offense. Allen Iverson has the second highest. He was brought in for offense purposes. That's what his job was, period. Allen Iverson has the second highest scoring average. So, Michael Jordan's career average is 30.1. What symbol would I use for that? Did they look at all the games he played? Well, yes, they did. And what did they want to know? How many points did he score this game, the first game? How many points did he score the second game? Can I do arithmetic with that? Yes, I can. This makes this a mu. mu. The average of everybody, average of all his games. The annual report of Spectrum indicated 43% of the people have the subscribers have the HBO movie package. Does the annual report contain everything? Yeah, everything for this year for this company. Most annual reports, what they're reporting are population parameters. What question did we ask? Do you have the HBO package? Yes or no? Yes or no? Yes or no? And I do arithmetic with S's and No's. No. Makes this a P. And lastly, Amgen reported the new drug increased life expectancy by 5 years. Did they test the drug on everybody? Well, they tested the drug on everybody that they tested it on. See, here's your problem. Are they going to use this to talk about just those people? Or are they going to use it to talk about how well this drug's going to work in general? How effective this drug is in general? They're going to use it in general. That's the reason we're studying it. So this is a sample. And I get back what? Numbers, 5 years, 4 years, 6 years, 7 years. So this is a X bar. So now you'll be able to tell what symbol are, when you read a report which has some technical information, what symbol were they talking about? About 25% of your 302 exam is this stuff right here. It is recognizing whether it's X bar, mu, P, P hat. So you're going to need to know that when you hit 302. Okay, so let's take a look at an example here. Let's do 2 more examples and we're out of here. Page 15, number 1. Kenny C. McCrack. I wrote this one. I know it's hard to tell. Owns 12 hip, hop, hip, hold on here, I gotta read this. Hip, hop, hip hugger fashion stores, specializing in the full moon line of lowrider pants. some gravity defying pants. I don't know how some are staying up. This is a mystery to me. Each store maintains its own inventory of items. Kenny has paid for a full financial audit. What's a full financial audit? It's a census. Where we go out and we look at everything. And we have the inventory values for these 12 stores, and they're in thousands of dollars, 85,000, whatever. So we take data, and it's, of course, quantitative data. We take the data, first thing we do is we sort it. We get it in order, and what should pop out of that right away is our sample mode, which would be, we had 3 spots of 85 as our sample mode, the most often seen. And there are 12 in our population, so I go down 1, 2, 3, 4, 5, 6. Okay, 2, 4, 6 right here. So right here in between, here's the top 6 and the bottom 6. Right here in between the 85 and the 86 is where the fold would go. So our median is between the 6th and the 7th value. 85 plus 86 over 2 is 85.5. We add them all up and divide by 12. We get the 86, and it is a census, so we would call that mu. Our measures of variability or dispersion, I take the square of the difference of each value and the mean, or I take the absolute value of each value and the mean, and the sum of the squares is 120, sum of the absolute values is 30. Dividing the 120 by 12, I get 10 as the variance. Dividing the 30 by 12, I get 2.5 as the mean absolute deviation. when you take Operations Management Business 306, you'll use this one a lot for forecasting accuracy. The square root of the 10 is the standard deviation, the population standard deviation, and our range, highest minus lowest, 92 minus 80 is coincidentally 12. Here's the histogram of it. Okay, I should have said draw the histogram with a interval of $2,000. So this would be a histogram with the interval. The width of our unit over here is 2,000. So we go from 80 to 82. There is one that has an observation that is bigger than or equal to 80, but less than 82. So that's how you read this. There is one that is bigger than or equal to this attack mark here, but less than this one. There is one that is bigger than or equal to 84, but less than 86. There is a 4 that is bigger than or equal to 86, but less than 88, and so on. So we have a distribution that is, looks like a slight skew to the right. It doesn't look exactly symmetric. It looks like there's a little ski jump going over here to the right. So was our mean a little bigger than our median? Well, yes, it was. 86 is the mean and the median 85.5. So we'd say we have a slight skew to the right. If we look at the cumulative, so there is one that is 80 or less, that is greater than or equal to 80 but less than 82. There is 2 that is greater than or equal to 80 but less than 84. There is 6 that are greater than or equal to 80 but less than 80, 86 or 88 here, I've lost count. And this is called the cumulative distribution or cumulative histogram. And this kind of curve here that's like a stretched out S is referred to as an ogive curve. So a stretched out S curve is called an ogive curve. Kenny has a potential buyer for the chain. Being a prudent person, this person conducted an independent survey, but didn't have enough money to look at all the stores and only looked at 5 of them at random. And we got the results 85, 88, 82, 88, and 92,000. So this data is from a sample, not a census. Sort the data, do the exact same stuff. What's the mode of the sample? Most often seen value is 88. What is the median? Since we have an odd number, 1, 2, 3, 4, 5, it's going to cut right through the middle one when we fold it, 88. Add them up, divide by 5, we get 87. Is the 87, the X bar, exactly equal to what we saw for the mu? No, not quite. But it should be close. And we'll see in the second half of the course that when we take samples, the bigger the sample, the closer our sample mean will be to the real population mean. Bigger the sample, the closer it is, or the more accurate it is. What is our range? High minus low, 10. Find the sample variance and standard deviation. You can see it. Great stuff. Okay, so this is just an illustration of the mechanics involved in finding these descriptive statistics for both a census and a sample. Okay, our last problem for the day. Let's take a look at, I think it's our last problem. Page 15, number 3. Carcinogen sampled the amount of mercury in swordfish at 11 different seafood markets in LA and got the following results. So I take the data, what do I do with it? I sort it. And Looks like I got a mode of 39. There's 2 of those, and no other reps. I don't see any reps. Okay. Oh, halfway at 11 in our sample, so that cuts it in half. If I take this group of 5 here and say, treat it like a separate little sample, what's the median of that group? 36. If I take this group here and say, what's the median of this group? 56. That's Q1, Q2, and Q3. The 25th percentile is 36. 50th percentile, 45. The 75th percentile is 56. And when I give you 9, 36, 45, 56, and 90, I've given you the 5-number summary. Smallest, Q1, Q2, Q3, largest. That's called the 5-number summary. Tells us a lot. If I do a stem and leaf, so here I have the numbers 0 through 9, 10 through 19, and so on and so on. I have one observation of 9. I have an observation of 18. I have a 36, a 39, and a 39. I have a 45, a 46, and a 47. Get it? You know, you strip off the tenths and just do with the units, but put it in its proper position. That's called a stem and leaf. If you have like a couple hundred observations or less, it's not a bad way to do it. In fact, it's an improvement on your histogram. If I flop this over, if I switch this 90 degrees, do a 90-degree rotation here, and look at this, what do we got? I got the histogram. This is the frequencies here, and here's your x-axis, here's the frequencies. So it's a histogram with actual numbers on it. So you can see not just bars, but actual numbers, what happened. So if you have a couple hundred observations or less, it's not a bad thing to do. It's an improvement on the histogram. And lastly, we have the box plot. The box plot is used to find outliers. And there was a book written by Malcolm Baldrige called Outliers. And what he did was study truly exceptional people, people who were truly exceptional at what they did. And he came up with what's called the 10,000 hour rule. You want to be great at something, come back after you've done it 10,000 hours and we'll see how good you really are. That's what they all had in common, of those people who truly were exceptional at doing something. And he looked at people in industry and other fields, not business, and came up with this idea of he called it outliers. And it's based upon this statistical technique of finding people that are truly exceptional, that are truly maybe not be of the regular population, that may be normal. Now, outlier may be something very good or something bad, depending. You don't know. I mean, if it's, in this case, he was talking about people who did exceptionally good things, but an outlier could be something that's really bad also. It just means it's a little bit too high or too low to fall into the norms we would have expected. Malcolm Baldrige also wrote the book Tipping Points, which is how small things, when they accumulate, end up making dramatic changes where things become to the point you can't forecast them anymore. And there's some discussion that I told you about that in the first class, that we are in the 4th industrial revolution and are about to hit a couple tipping points. So here we go. It's called the box plot. The box goes from 36 to 56. And what was the 36 again? Q1. What was the 56 again? Q3. 25% of them fall below 36. 25% of them fall above 56. It's the 25th percentile and the 75th percentile, so by definition, 50% of them are in the box. Now, if we take this distance here, 56 minus 36, or 20, the distance in this width of this box, and extend that out, and my drawing is not drawn to scale at all, because it should be 1.5 of those. It should be this long here. My my whisker should go this long, and then another half should go out, maybe out to here, but I couldn't get it on the page. So it should be over here, but it is what, 20 below, not 20 below, 30 below, 1.5 times 20. So 1.5 times 20 is 30. 36 minus 30. The lower bound here would be a 6, and the upper bound here would be an 86. Those are called the whiskers. Half of the people are in the box, and almost all of the other times, you know, well over 99% of the time, they should we should capture in the box or the whiskers everybody. If you're above this top point 86 or below the lowest point 6 that we would ever expect, you are called an outlier. You are truly exceptional for some reason. We have one outlier, and it's a 90. So what do we do with outliers? We go back and retest them. Maybe we made a mistake on this person. What are we talking about? Swordfish here in Mercury. Okay, so maybe we got the swordfish that, what was the, in The Simpsons, the three-eyed fish name? What was that? Blinky? Blinky the fish? Anyway, it lived behind behind the atomic energy plant. It lived there and had 3 eyes. Anyway, so maybe we snagged a fish like Blinky living in some polluted area. So these need to be looked at, make sure that there wasn't a problem with our instrumentation, make sure we haven't made an error, and then if they are exceptional, then they need to be dissected and say, let's look at this person, dissect them completely as something to emulate as being good or something to avoid if it's bad. All right. And then I relate this idea of the box plot and these whiskers as if it were a normal distribution. Our data in this case is not normally distributed, but if it were, then we would be talking about almost 3 standard deviations to the left and the right to get to these exceptional people. A couple more topics to go over. I'll do this next time. I think I beat you enough for now. I'll save this for next time. Practice problems for 2 weeks from today. Try to do problems 2 and 4. Also, memorize your symbols for 2 weeks from today. See you next week.